Hello everyone, today we will discuss a medium hard level binary tree problem by using dynamic programming algorithm. This is the LeetCode algorithm problem 96, unique binary search trees. Firstly, let's see the description of this problem. Given an integer n, return the number of structurally unique binary search trees which has exactly n nodes of unique values from 1 to n. Firstly, let's define the dynamic programming function DPI, which will calculate the number of unique binary search trees for I nodes. Then we need to find the basic pattern to calculate the dynamic function DPI. Here is a trick. DPI only depends on the number of nodes I, but we don't need to consider the specific values of each node. For example, 3 nodes 1, 2, 3 and another 3 nodes 2, 3, 4 will create the same number of binary search trees. Then we define function f. Fji calculates the number of unique binary search trees, where j is the root and the total number of nodes is I. Here is our explanation. J is the root, and we have node 1, node 2 until node j minus 1 to form the let subtrees, and we have j plus 1, j plus 2, and the largest node I to form the right subtrees. Here we have j minus 1 nodes to form the subtrees. Then we will have dpj minus 1 number of unique binary search for j minus 1 nodes. And because DPI only depends on the number of nodes, but we don't need to consider the specific values of the nodes. So from j plus 1 to I nodes, there are I minus 1 nodes, so we have dpi minus j number of unique binary search trees for the right subtrees. Then we need to calculate how many unique binary search trees for the total I nodes by using node j as the root. Firstly, if we fix one left subtree, and then we can have dpi minus j choices to form the entire binary search tree. For any subtree, left subtree structure, we have dpi minus j choices as the right subtree. Then we have dpj minus 1 choices for the left subtree. So to form the entire subtree, we have dpj minus 1 here multiplies dpi minus j. This number of unique binary search trees for I as the total node number and the j as the root for the tree. Then we will have dpi equals f0i, which is j equals 1, which means node 1 as the root, and f1i, which means total node number is I, and node j, which is 2 as the root, until fni. And this is dp0 times dpi minus 1 plus dp1 times dpi minus 2 until the end. So to calculate DPI here, we have for loop where in each iteration DPI equals itself plus dpj minus 1 times dpi minus j. So for each I nodes, we have dpi equals the sum of the dpj minus 1 times dpi minus j. So we can calculate dp2, which is the number of unique binary search trees for 2 nodes, and dp3 until dpn. Then we will have the list dp. Here we have dp0 to dpn. There are n plus 1 numbers for the dp list. And then the special cases include dp0, which is 1, and dp1, which is also 1. So for 0 nodes, we have only one structure, and for 1 node, we only has one structure as well. Then we have dp0, dp1, dp2 until dpn by using this 2-layer for loop. And then for n nodes, we will have the result dpn and return it. In this way, we solve this binary search tree problem by using dynamic programming algorithm. And our time complexity is O(n) squared because we have the 2-layer loop here. And the space complexity is O(n) because we need to store the dp list, which is from dp0, dp1 to dpn, and then we will have space complexity as O(n). That's all for today. Thank you so much for your time. Bye bye.